This is section 15.9 on change of variables in multiple integrals. This section can get really long, so I try to make it as painless as possible for you for this particular section. All right, so page 1052, 15.9. We're trying to do by analogy. If you look at number one, integrate from a to b of f of x dx. And by means of a substitution, you can integrate from c to d of f of g of u, g prime of u, du. So in other words, you might recall in Calc 1 and 2, you could integrate originally from, say, 3 to 5. Then after you make a substitution, you might integrate from 7 to 24 all of a sudden. Okay, so one interval becomes another interval, but that becomes much more complicated once you get to multivariable calculus, because in Calc 1 and Calc 2, you're basically going from one interval to another interval. So an interval from A to B becomes an interval from C to D. But page 1053, you could have figure 1, you could have that brown one or yellow one going to the blue one, or vice versa. T stands for a transformation. By means of a transformation, 2-dimensional or 3-dimensional, you might have some region like this ending up with a region like this. Okay. Page 1054, you might have a square region ending up like that. And the arrows, which we're going to use also, are indicating what happens to each of these segments. So 1 arrow, 2 arrows, 3 arrows, 4 arrows. That 1 arrow becomes this 1 arrow. The 2 arrows becomes this curved here. The 3 arrows becomes that, and the 4 arrows becomes the 4 arrows here. So you can see there's a much richer variety of possibilities once you get to multivariable. Again, so in Calc 1 and 2, you just had one interval from here to here, and it moves over to here to here. But now once you get to 2 dimensions or 3 dimensions, a whole new world of possibilities opens up, where you could have something like this, and you get with something like this. Okay, or figure 3, something like this, ending up like this. Again, they can get really, really bad. I'm only going to give you the quote unquote nicest ones, the ones that hopefully aren't so bad. All right, so first thing we have to do is define some terms. Okay, on page 1055, we define something called the Jacobian. I will abbreviate with capital J. Okay, this is a 2-dimensional Jacobian. It looks like the partial of xy with respect to uv. It's basically a 2 by 2 determinant. Okay, it's the partial of x with respect to u and v over the partial of y with respect to u and v. And you work it out like a 2 by 2 determinant. It's that minus that. Okay, so it looks at the partial of xy with respect to uv. It's, you take x and y and differentiate with respect to u and v. So partial of x with respect to u, partial of x with respect to v, and partial of y with respect to u, partial of y with respect to v. So it's a 2-dimensional Jacobian. Okay. The 3-dimensional Jacobian, by analogy, page 1059, you can put that on your cheat sheet. Partial of x, y, z with respect to u, v, w, and you can see it's a 3 by 3 determinant, which you also know how to do. It's the partial of x, y, and z with respect to u, v, and w, and you work it out just like any of the other 3 by 3 determinants, where you take out the top row and cover that row and column, and you take these 4 minus this one, and you block out that row and column, and you have these 4, and then plus this one, block out that row and column, and you have these 4. Okay, so you have something called a Jacobian. What is this Jacobian good for? It's basically the multiplication factor. So remember back in Calc 1 and Calc 2, suppose you had let u equal x cubed, du equals 3x squared dx. So you can't just change du to dx. You have that extra multiplication factor of 3x squared. That extra multiplication factor 3x squared in multivariable is called the Jacobian. It's the extra thing that you have to multiply by. Okay, so when you're going from x, y to uv, you have to multiply by the absolute value of the Jacobian. That's sort of like the du equals 3x squared dx. Okay, that you have going on here. Now they give you a justification of this, but it's when you change from one coordinate system to the other, Okay, the little change in area isn't quite the same. Okay, so this thing coming in here, the area is not necessarily the same. Okay, so they did some analysis with a vector A and a vector B. And you might recall that the magnitude of the cross product gives you the area of the parallelogram determined by the two vectors. So they cross them, RU cross RV, all the analysis there if you want. But essentially, what it comes out to be is the Jacobian. It's the extra multiplication factor that you have. So in a nutshell, when you change from one variable system to another, this is what you want to put on your formula sheet. Whoops, 1056. Although you're not really going to have to do too many. This can get really, really long. All right. So double integral of f of x, y, dA. It's well behaved. Well behaved means it follows all of these rules here. Okay. So they will give you a definition of x, a function of u and v. Y is a function of u and v. So dA, dx, dy becomes du, dv times the extra multiplication factor, which is the absolute value of the Jacobian. Okay, so that's like u equals x cubed, du equals 3x squared dx. That 3x squared is your Jacobian. It's the extra multiplication factor that you have. Okay. And the three-dimensional flavor, page 1059. dv, so x, y, z, they switch it to u, v, w. Again, you multiply it by the absolute value of the Jacobian, the partial of x, y, z with respect to u, v, w. Okay. Again, I don't give you too many of those problems because it's going to be really, really long. Oh, here's a nice little picture. Okay, I mean, this is bad enough on page 1058, but you could have this region in u and v ending up looking like that in x and y. Okay. So very rich possibilities of what could happen. Okay, and a side note, as you might guess, okay, when you go to cylindrical coordinates from x, y to r theta, x is r cosine theta, y is r sine theta, they did the Jacobian over here, it comes out to be r. The extra multiplication factor is r, which is precisely the reason why when you go from Cartesian coordinates to cylindrical coordinates, f of x, y, dx, dy, or dy, dx. Okay. F of r cosine theta, r sine theta, Jacobian, dr, d theta, the Jacobian comes out to be r, which is why dx, dy becomes r, dr, d theta. Okay. And can you guess what happens in spherical coordinates, which we just finished? Higher dimensional. So we have this. If you find a Jacobian of this transformation, x is rho sine phi cosine theta, y is r sine phi sine theta, z is rho cosine phi. So the partial of x, y, z with respect to rho, theta, and phi, based on that, you don't have to look at this closely at all if you don't want to. I'm not holding you responsible for it. They work this all out. Okay, the Jacobian comes out to be negative rho squared sine phi, whose absolute value is rho squared sine phi. And that's precisely from what we would call from the last section. That's why dv, which is dz, dy, dx in some order, becomes rho squared sine phi, the Jacobian, well, the magnitude of the Jacobian, d rho, d theta, d phi. Okay. And I accidentally did something there. Okay, but then the hardest part of this section is to see what happens when you change from one coordinates from x, y to u, v, or vice versa. Some of these problems can get really, really long. So let's try to get our feet wet and get started with them. Okay, so 15.9, page 1060. There were not that many problems. Finding a Jacobian is pretty straightforward. The transformation problems can get pretty bad. Okay. And then do a problem all the way through from start to end, it can get really, really bad. Okay, so I try to do as much of that as possible. Okay. All right, so number one, transformation, x is 2u plus v, y is 4u minus v. Again, this is just like in Calc 1 and Calc 2, let u equal 3x squared. Okay, but here, x and y are defined as u and v. Okay, so Jacobian, by definition, is the partial of x, y with respect to u, v, partial of x with respect to u and v, partial of y with respect to u and v. So partial of x with respect to u is 2, partial of x with respect to v is 1, partial of y with respect to u is 4, partial of y with respect to v is -1. So we have that times that is -2 minus 4. The answer is -6. That's all. Okay, then I did a three-dimensional Jacobian for you. X is uv, y is vw, z is wu. So the Jacobian is a partial of x, y, z with respect to u, v, w. So partial of x, y, and z with respect to u, v, and w. So partial of x with respect to u, v. Partial of x with respect to v, u. Partial of x with respect to w, there is no w, 0. Partial of y with respect to u, there is none, so 0. Partial of y with respect to v is w. Partial of y with respect to w is v. Partial of z with respect to u, w. Partial of z with respect to v, there isn't any, so 0. Partial of z with respect to w is u. So it's v times something minus u times something plus 0 times something. Well, 0 times something, I don't have to worry about it. So v, cover this up, wv 0u minus u 0vwu. So we have v times that minus that, uw minus nothing, minus u times nothing minus vw. So I have uvw minus a minus uvw, 2uvw. Okay. Now for an actual transformation, okay, this can get really, really bad. Okay, so you have 0,2 cross 0,3 in u and v, and the transformation is x is 2u plus vv, y equals u minus v. Okay, now the easy thing to do is just plug in. So I plug in u and v 0, 0, you end up with 0, 0. You plug in 3, 0. So 3 goes there, 0 goes there. That gives me 6 for x. 3 there, 0 there gives me 3 for y. So 6 comma 3. 3, 2. 3, 2. 6 plus 6 is 12. 3, 2. 3 minus 2 is 1. So 3 comma 2 goes to 12 comma 1. 0, 2. 0, 2 gives me 6. 0, 2 gives me -2. So 0, 0 stays at 0, 0, but 3, 0 in uv becomes 6, 3 in x and y. 3, 2 in u and v becomes 12, comma 1 in x and y. And 0, comma 2 in u and v becomes 6, -2 in x and y. So here are the points in x and y, 0, 0, 6, 3, 12, 1, 6, -2. Now I drew it linear. We haven't proved that it's linear. This does turn out to be what's nice, a linear transformation. Everything here is linear, but we haven't proved it. To actually prove it, here we go. So I decided to call it L1, L2, L3, and L4. So 1 arrow, 2 arrows, 3 arrows, 4 arrows. Well, how do I know this isn't curved or something like that? Okay, so 1 arrow, 2 arrow, 3 arrows, 4 arrows. Okay, so L1, V is 0, and u is going from 0 to 3, it looks like.